Have you ever wished you could go back and fix a mistake? Maybe change that one moment where everything went wrong? We've all been there, lying awake at night, replaying that conversation, that decision, that split second where life took a turn. It's a deeply human feeling, this desire to rewind time, to have a second chance. Hollywood feeds this dream with countless movies about time machines and alternate timelines, and we eat it up because deep down, we all want to believe it's possible. We imagine ourselves stepping into a sleek machine, dialing back the years, and emerging in a world where we can change everything. The fantasy is seductive. It promises us control over the one thing we can never truly control, the past. But here's the uncomfortable truth that most people don't want to hear. Time travel to the past isn't just difficult or beyond our current technology. It's fundamentally impossible. Not because we haven't built the right machine yet, but because the universe itself, at its deepest level, simply doesn't work that way. And the person who helped us understand this uncomfortable reality was Richard Feynman, one of the most brilliant physicists of the 20th century. Feynman had a gift for cutting through the fantasy and revealing the simple, undeniable facts about how nature operates. He didn't deal in science fiction, he dealt in science fact. And the fact is this: the laws that govern our universe make traveling backward in time an impossibility, not improbable, not just really hard, impossible. This isn't about pessimism or crushing dreams. It's about understanding something profound and beautiful about the nature of reality itself. The universe has rules, fundamental rules that cannot be broken, and time travel to the past violates every single one of them. Today we're going to explore why. We're going to journey through the science that Feynman helped develop, the principles that govern time and causality, and we're going to discover that the reason time travel doesn't work is actually far more interesting than any science fiction story. Because the truth about time is stranger, more profound, and more beautiful than any fantasy we could imagine. Now you might be thinking, wait a minute, haven't scientists talked about time travel? Didn't Einstein's theory show that time is relative, that it can bend and stretch? Don't physicists discuss things like wormholes and closed time-like curves? How can you say time travel is impossible when there are scientific papers written about it? These are excellent questions, and they reveal something important. Most people confuse two very different concepts. Yes, Einstein showed us that time is relative. Yes, time runs at different rates, depending on how fast you're moving or how strong the gravitational field is around you. If you travel close to the speed of light and then return to Earth, less time will have passed for you than for the people who stayed behind. This is called time dilation, and it's real, proven, measured. GPS satellites have to account for it every single day. But here's the crucial distinction. Moving forward in time at different rates is not the same thing as moving backward in time. Not even close. When physicists talk about theoretical time travel scenarios, they're discussing mathematical solutions to equations, not practical possibilities. They're exploring what the mathematics allows in abstract space, not what the universe actually permits. It's like discovering that the rules of grammar technically allow you to write a sentence that's 1,000,000 words long. Sure, the rules don't explicitly forbid it, but that doesn't mean you should try it or that it would serve any useful purpose. The question isn't whether we can write down equations that seem to permit time travel. The question is whether the universe, in its actual physical implementation, allows it. And the answer, when you dig into the deeper principles that Feynman and others uncovered, is a resounding no. The universe has a direction, an arrow, a one-way street built into its very fabric. We call this the arrow of time, and it's not just a suggestion. It's a fundamental feature of physical reality, as real and as unbreakable as any law in physics. Let's start with something simple, something you experience every single day, but probably never think about. Pour cream into your coffee and watch what happens. The cream swirls, spreads, and within moments, you have a uniform mixture. The cream doesn't stay separate. It doesn't eventually mix itself and return to being a distinct blob. Once it's mixed, it stays mixed forever. This seems so obvious, so natural that we don't even question it. But why? Why doesn't the cream spontaneously separate? After all, the individual molecules of cream and coffee are just bouncing around randomly, following the laws of physics. In principle, if every single molecule just happened to move in exactly the right way, at exactly the right moment, the cream could separate back out. The laws of motion for individual particles don't forbid this. Newton's laws work exactly the same, whether time runs forward or backward. If you filmed a single particle bouncing around and played the film in reverse, you couldn't tell the difference. The math is the same, but when you have billions upon billions of particles, something remarkable happens. The purely random motion of all those particles creates an overwhelming statistical preference for disorder. This is the second law of thermodynamics, and it's arguably the most important law in all of physics. It states that entropy, which is essentially a measure of disorder or randomness, always increases in a closed system, always, without exception. This isn't just a good idea or a helpful guideline. It's an iron law of nature. The great physicist Arthur Eddington once said, "If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." Now let's connect this to time. The reason cream doesn't mix from coffee isn't because it's physically impossible for every molecule to move in the right way. It's because the number of ways the molecules can be mixed vastly, astronomically, outnumbers the number of ways they can be separated. If you calculated the odds of spontaneous UN mixing, you'd get a number so small that the entire age of the universe wouldn't be enough time to wait for it to happen, even once. This is what entropy means. Mixed cream and coffee has higher entropy than separated cream and coffee, and entropy always increases. This is the arrow of time. It's the reason eggs break, but don't spontaneously reassemble. It's the reason ice melts in warm water, but warm water doesn't spontaneously freeze and heat up simultaneously. It's the reason you remember the past, but not the future. Memory itself requires entropy increase. To form a memory, you have to encode information, which means arranging molecules in a specific order, and that process creates entropy elsewhere. Everything that makes time feel like it flows in one direction, every experience you have of causality, of before and after, of cause and effect, is rooted in this thermodynamic arrow. Now, I want you to pause for a moment and think about this question. Have you ever wondered what would actually happen if time travel were possible? Not in a movie, but in real life. What would it mean for causality? For cause and effect? For the very structure of reality? Drop your answer in the comments below. And while you're thinking about it, think about this. If you could go back in time, would you actually want to? What if changing the past meant erasing everyone and everything that came after that moment? This is where we start to see the problems multiply. Because time travel doesn't just violate thermodynamics, it tears apart the very fabric of causality itself. Consider the famous grandfather paradox. You travel back in time and accidentally prevent your grandparents from meeting. If they never meet, your parents are never born. If your parents are never born, you're never born. If you're never born, you can't travel back in time to prevent your grandparents from meeting. It's a logical loop with no resolution. Some people try to solve this by proposing parallel universes or alternate timelines. They say, well, maybe when you go back and change something, you create a branch in reality, a new timeline where things happen differently. But this doesn't solve the problem, it just hides it. If going back in time creates a new universe, then you haven't actually changed your past. You've created a different universe with a different past. Your past still happened exactly as it did. You're just now in a different reality. And if that's the case, then what you're doing isn't really time travel. It's universe hopping or reality switching. True time travel means affecting the actual past that led to your present. And that's where the contradictions become insurmountable. Feynman understood this deeply. He didn't just think about time as a mathematical dimension. He thought about it in terms of process, causality, and the sequence of events. In quantum mechanics, which Feynman revolutionized with his path integral formulation, particles don't just follow one path from point A to point B, they explore all possible paths simultaneously. But even in this quantum weirdness, causality is preserved. The future depends on the past, never the reverse. Now let's bring Richard Feynman fully into this story, because his insights cut right to the heart of why time travel fails at every level of physics. Feynman was born in 1918 in New York City, and from childhood he had an obsession with understanding how things really work, not just memorizing what people said about them. His father instilled in him a deep skepticism of authority and a hunger for genuine understanding. This attitude shaped everything Feynman did in physics. He had zero patience for empty formalism or mathematical manipulation that didn't connect to physical reality. When he looked at a problem, he always asked, "What is actually happening here? What are the particles doing? What does this mean in terms of real events in the real world?" This approach led him to completely reformulate quantum mechanics in the 1940s. The traditional approach, developed by people like Heisenberg and Schrödinger, used wave functions and operators and abstract mathematical machinery. Feynman found a different way, a way that focused on the actual paths particles take through space and time. In his path integral formulation, you calculate the probability of a particle getting from point A to point B by considering literally every possible path it could take, assigning each path a certain quantum phase, and adding them all up. It sounds crazy, but it works perfectly, and reveals something profound about how quantum mechanics respects causality, even while embracing uncertainty and probability. In Feynman's picture, particles always move forward in time. Every path, every possible trajectory goes from an earlier time to a later time. You never have paths that loop backward. Why? Because such paths would violate causality. They would allow effects to precede causes. Feynman took this so seriously that he proposed a radical idea. Antiparticles, like positrons, are actually ordinary particles moving backward in time, but even this doesn't give us time travel in any useful sense. An electron moving backward in time looks exactly like a positron moving forward in time. The net result is still a universe where causality flows in one direction, from past to future. There's no way to send information backward, no way to change what already happened. Feynman also worked extensively on quantum electrodynamics, the quantum theory of light and matter, which earned him the Nobel Prize in 1965. This theory is stunningly accurate. It's been tested to something like 10 decimal places, making it the most precisely verified theory in all of science. And in all of that precision, in all those calculations involving particles popping in and out of existence, virtual particles, quantum fluctuations, and all the weirdness of the quantum world, causality is never violated. Not once, not even a little bit. Effects always follow causes. The future always depends on the past. The arrow of time is absolute. Feynman understood that this isn't just a feature of our current theories. It's a fundamental requirement for any theory that describes a consistent, comprehensible universe. If effects could precede their causes, if you could travel backward in time and change events, then prediction becomes impossible. Science becomes impossible. Logic becomes impossible. The universe would be not just chaotic, but literally incoherent, a jumble of contradictions with no stable structure whatsoever. Let's dig even deeper into the quantum level because this is where things get truly fascinating and where Feynman's insights shine brightest. At the quantum scale, Particles exhibit behaviors that seem utterly bizarre from our everyday perspective. Electrons can be in two places at once, or more accurately, in a superposition of many positions simultaneously. Particles can be entangled, meaning measuring one instantly affects the other, even across vast distances. Quantum mechanics is weird, undeniably weird, and this weirdness has led many people to speculate that maybe, just maybe, quantum effects could enable time travel. But here's where Feynman's careful thinking becomes crucial. Yes, quantum mechanics is strange. Yes, it defies our intuitions, but it doesn't violate causality. The most important principle in quantum mechanics, the one that underlies everything else, is unitarity. Unitarity is a mathematical property that ensures probabilities always add up to 100%, and that information is conserved. But more fundamentally, unitarity ensures that time evolution is reversible in principle, but directional in practice. You can write down the equations that describe a quantum system and technically run them backward, just like Newton's equations. But when you do, you're not describing time travel. You're describing the inverse process. If you know the current state of a quantum system perfectly, you can in principle calculate what its state was in the past. But you can't go back and interact with that past state because you're not actually there. You're just calculating, just reconstructing information. There's a profound difference between calculating what the past was and traveling to the past. The calculation happens now, in the present, using information that exists now. True time travel would mean physically existing at an earlier moment, interacting with it, potentially changing it, and that's simply not what the mathematics describes. Feynman spent years teaching quantum mechanics, writing famous lectures that are still used today, and in all of those teachings, he emphasized one point repeatedly. Quantum mechanics doesn't let you send signals backward in time. You can have quantum entanglement, where measuring one particle seems to instantly affect another far away. But you can't use this to send information faster than light or backward in time. The correlations you see were determined when the particles were created, not when you measured them. This is subtle but crucial. Quantum mechanics is weird, but it's not incoherent. It has rules, strict rules, and those rules protect causality absolutely. At this point, you might be thinking about wormholes, those shortcuts through space-time that appear in science fiction, and even in legitimate physics papers. Einstein's general theory of relativity, which describes gravity as the curvature of space-time, does indeed allow mathematical solutions called Einstein-Rosen bridges or wormholes that connect two distant points in space and time. Could these be time machines? On paper, if you could stabilize a wormhole and manipulate its ends properly, you could in principle create a path that leads to your own past. Physicists like Kip Thorne have explored these ideas rigorously. But here's where physical reality asserts itself against mathematical possibility. To create a stable wormhole, you need something called exotic matter, which is matter with negative energy density. This isn't just rare or hard to produce. As far as we know, it doesn't exist in any form that could be used to stabilize a macroscopic wormhole. Yes, quantum effects can create tiny regions of negative energy for incredibly brief instants. But scaling this up to stabilize something you could travel through is beyond anything we can imagine with known physics. But even if you had exotic matter, even if you could somehow build a wormhole, you'd run into another problem, the chronology protection conjecture. This was proposed by Stephen Hawking, and it suggests that the laws of physics actively prevent the formation of closed time-like curves, the technical term for time travel paths. Why? Because whenever you try to create such a curve, quantum effects build up exponentially, creating a runaway feedback loop of energy that would likely destroy the wormhole before it could be used. Imagine trying to create a time machine. As you get closer and closer to completing it, quantum fluctuations that have traveled through the wormhole start interacting with themselves, building up energy, creating what physicists call a vacuum polarization effect. This energy would likely become infinite, or at least large enough to collapse the wormhole at the exact moment it becomes a time machine. The universe seems to protect itself against time travel paradoxes by making the machinery of time travel self-destruct at the critical moment. Feynman would have appreciated this deeply. It's an example of nature imposing consistency on itself, ensuring that the universe remains coherent and logical. You can write down solutions to equations that seem to allow time travel. But when you analyze what actually happens physically, including all quantum effects, the universe says no. Let's talk about the implications of all this, because understanding why time travel doesn't work tells us something profound about the nature of time itself. Time isn't just another dimension like space, even though relativity treats it mathematically as the fourth dimension. Time has a direction, an inherent asymmetry that space doesn't have. You can move left or right, forward or backward, up or down in space, but you can only move forward in time. Why is this? We've already discussed entropy and the thermodynamic arrow of time, but there are other arrows too. There's the cosmological arrow, the direction in which the universe expands. The Big Bang happened in our past, not our future. The universe is getting bigger, cooler, more spread out, and this expansion defines a direction to time on the largest scales. There's the quantum arrow, related to the collapse of wave functions when measurements are made. When you measure a quantum system, it goes from being in a superposition of many states to being in one definite state. This process is irreversible and defines a before and after, a past and future. All of these arrows point in the same direction, and that's not a coincidence. They're all ultimately rooted in the low entropy initial state of the universe at the Big Bang. The universe started in an incredibly special, highly ordered, low entropy state, and it's been increasing in entropy ever since. That increase drives everything we think of as time. Modern technology relies on this deep understanding of time and causality. GPS satellites, which use relativity to make corrections for time dilation, work because time has a consistent direction. The satellites experience time at a slightly different rate than we do on Earth's surface due to both their velocity and the weaker gravitational field they experience. But all the time, rates are running forward. Engineers don't have to worry about signals arriving before they were sent or causality violations. They just have to account for the relative rates of forward-moving time. Particle accelerators like the Large Hadron Collider smash particles together at nearly the speed of light, creating showers of new particles, some of which exist for only tiny fractions of a second. Physicists track these particles, measure their properties, and test quantum field theory with extraordinary precision. In billions upon billions of collisions, with particles appearing and disappearing, transforming and decaying, not once has anyone observed a violation of causality. Particles with shorter lifetimes don't affect the collisions that created them. Causes precede effects, always, without exception. Even in the bizarre world of quantum entanglement, which Einstein famously called spooky action at a distance, causality holds. When two particles are entangled, measuring one seems to instantly determine the state of the other, no matter how far apart they are. This freaked Einstein out because it seemed like information was traveling faster than light. But Feynman and others showed that no information actually travels. You can't use entanglement to send a message. You can only see correlations when you compare measurements afterward, using normal, slower-than-light communication. Causality is protected even in the weirdest corners of quantum mechanics. Before we wrap up, I want to ask you to do something. If you've found this exploration of time and reality fascinating, if you appreciate science that doesn't sugarcoat the truth or pander to fantasy, hit that like button. And if you want more content that digs into the deep, sometimes uncomfortable truths about how the universe actually works, subscribe to this channel. We're building a community of people who value real understanding over comforting illusions, and I'd love for you to be part of it. So, where does this leave us? We started with a simple human desire, the wish to change the past, to travel backward through time and fix our mistakes. And we've discovered that this desire, as deeply as we might feel it, crashes against the fundamental structure of reality. Time travel to the past doesn't fail because we lack the right technology or because we haven't been clever enough. It fails because time itself has a direction built into the very laws of physics. Entropy increases, causality flows forward. Quantum mechanics preserves information but doesn't permit backward signaling. General relativity might allow mathematical wormhole solutions, but the universe appears to protect itself from the paradoxes these would create through quantum effects that destroy time machines before they can function. Feynman spent his life helping us understand these truths. He developed the mathematical tools to describe quantum processes with unprecedented clarity. He showed us how particles interact, how forces work at the deepest level, how quantum mechanics and relativity fit together in quantum field theory. And through it all, one principle remained inviolate: causality. Causes precede effects. The past leads to the future, never the reverse. This might seem like a disappointment. We can't go back and change our mistakes. We can't visit historical events or meet our ancestors. But there's a deeper beauty here, a profound order to the cosmos that makes everything we experience possible. The fact that time has a direction is what allows for growth, for learning, for memory, for life itself. If time were reversible, if the past could be changed, then nothing would be stable. There would be no continuity, no coherent story to the universe, just chaos and contradiction. Instead, we live in a universe that makes sense, that has rules, that allows us to learn from the past and build toward the future. We can't change what has happened, but we can shape what will happen. That's not a limitation. That's the very foundation of meaning and purpose. Understanding this, really grasping why time travel doesn't work, isn't about crushing dreams. It's about seeing reality clearly, seeing the deep structure that makes existence possible. Feynman dedicated his life to this kind of clear seeing, this refusal to accept comfortable illusions in place of difficult truths. He taught us that nature is as she is, not as we wish she were, and that understanding her as she truly is brings a satisfaction far deeper than any fantasy ever could. The universe has spoken. Time moves forward, causes precede effects, entropy increases, and we, as conscious beings in this strange and beautiful cosmos, move with it, learning, growing, building, always forward, never back. That's not a limitation, that's the adventure.